All right, let's dive in. Today, we're cracking open the very devices that run our world. We're going to demystify the magic that happens inside the tech we use every single day, from its most basic parts all the way to its absolutely mind-bending future.
Just think about it for a second. Every time you click a mouse, type on a keyboard, or just see an image on a screen, it feels so simple, right? But underneath it all is this incredible, perfectly coordinated storm of activity. It really is a tiny miracle of engineering happening millions of times a second.
So that's the big question, isn't it? How does a chunk of metal and silicon take a simple command from you and turn it into this rich, complex digital world we all live in? What is really going on inside that box? Well, that's what we're here to unpack.
To get our heads around how it all works, we've got to pop the hood and look inside. You see, any modern computer, and I mean any of them, from a crazy powerful gaming PC to the phone in your pocket, is really built around just a handful of essential parts, all working together.
So first up, you've got the motherboard. The best way to think of this is like the central nervous system and the entire city map of the computer all rolled into one. It's this big circuit board where literally everything else plugs in. It's the superhighway that lets all the other parts talk to each other.
Now, if the motherboard is the nervous system, then the CPU, well, the CPU is absolutely the brain. The central processing unit is where all the real thinking happens. It grabs instructions from your software, figures out what you want it to do, and then boom, it does it. It's the workhorse that carries out pretty much every command.
And then we have the artist in the family, the GPU, the graphics processing unit. See, while the CPU is a jack of all trades, the GPU is a master of one. Its whole job is to handle visual information, rendering all those stunning graphics in video games, or making sure the video you're watching right now is perfectly crisp and smooth.
Okay, so what about RAM? Think of RAM as the computer's short-term memory, or maybe like its workbench. When you open an app, the computer pulls all the necessary data into RAM for super fast access. But here's the catch. RAM is volatile, which is just a fancy way of saying when you turn the power off, poof, everything on the workbench gets cleared away.
So if RAM is the temporary workbench, storage is the permanent library. This is non-volatile, meaning it remembers everything even when the computer is off. This is where your operating system, your apps, your photos, all your files, this is where they all live, just waiting to be picked up and put on that RAM workbench.
And that library has had a serious upgrade over the years. For a long time, we used hard disk drives, or HDDs. They're basically like tiny record players with a spinning disk and a little arm that reads the data. But today, most of us have solid-state drives, or SSDs. The huge difference? No moving parts. It's all flash memory, which makes them way faster, tougher, and a whole lot more efficient.
Okay, so we know the parts now. We've met the whole team. But how do they actually work together to get anything done? Well, that brings us to the computer's grand plan. This really simple, logical flow that turns what you do into what you see.
Believe it or not, every single thing a computer does can be broken down into this simple four-step dance. First, it takes an input. That's you clicking the mouse. Then, the CPU gets to work and processes it. After that, it gives you an output, the thing you wanted to happen on the screen, and finally, if needed, it saves the result to storage. Input, process, output, storage. That's it. That's the blueprint for everything.
But let's zoom in on that process step, because that's where the real magic is. Inside the CPU, there's this relentless little three-step cycle happening at a speed that's just impossible to imagine. Billions of times a second, it will fetch an instruction, decode it to figure out what to do, and then execute it. Fetch, decode, execute, over and over and over. That's the engine that drives all of modern computing.
But that little engine, that CPU, wasn't always so little. For decades, the machinery to do this stuff took up entire rooms. And this quote here, it just nails the big turning point, the invention of the integrated circuit. That was the moment we started to shrink all that power down, the moment computers started on their path to being for everyone.
And that leads us perfectly into this incredible story of miniaturization. It's a journey of how we went from machines that filled up buildings to the ridiculously powerful devices that we carry around in our pockets today.
So, this evolution happened in a few giant leaps. Back in the 40s, you had massive computers running on these big, hot, unreliable vacuum tubes. Then the 50s gave us the transistor, which was a game changer, smaller, faster, much more dependable. In the 60s, we got the integrated circuit, which let us cram thousands of transistors on one chip. And then came the 70s, and with it, the microprocessor, an entire CPU on a single tiny slice of silicon.
And just to put that into perspective for you, by the middle of the 1970s, engineers could cram over 100,000 transistors onto a chip smaller than your fingernail. It was that kind of exponential growth that really lit the fuse for the personal computer revolution. And all that progress, all that shrinking and speeding up, has brought us to where we are today, what a lot of people are calling the 5th generation of computing. And this era, it's not just about being smaller or faster anymore. Now it's all about being smarter. We're in the age of intelligence. Yeah, the whole point of this 5th generation is to build machines that can actually understand us, that can learn from new information and adapt all on their own. We're moving away from just telling computers what to do, and we're building systems that can figure things out for themselves. Every time you talk to Siri, or use ChatGPT, or see a self-driving car navigate a street, that's the 5th generation right there in front of you. So where do we go from here? What's the next great leap? Well, it looks like it might involve leaving behind the simple ones and zeros, the binary code, that have been the foundation of computing from the very beginning. We are staring at the next frontier, computing that goes beyond binary.
And there are a few really mind-bending paths forward. You've got quantum computing, which uses weird physics where a bit can be a 1 and a 0 at the same time, letting it solve problems that are flat out impossible for even the biggest supercomputers. Then there's neuromorphic computing, which tries to build chips that are structured just like a human brain, making them incredibly efficient for AI. And then you have nanotechnology, building things atom by atom to shrink computers down to scales we can barely even imagine.
Look, if you want to understand the power of quantum, just look at this number. A few years back, Google's Sycamore quantum computer solved a problem in 200 seconds. Okay, fine. But get this. That same problem would take the world's fastest supercomputer an estimated 10,000 years to figure out. That's not just better, that's a whole new ballgame.
And this isn't some far-off sci-fi dream. It's happening right now. This quote here really brings it home. These technologies are going to reshape, well, everything. The only real question is whether you're going to be ready for it. So, we've gone from simple circuits to that relentless fetch-to-code-execute cycle, all the way to the edge of true artificial intelligence and quantum leaps. And it leaves us with one final big question to chew on. For their entire history, computers have just been amazing tools that follow our instructions. But what happens? What does it really mean for all of us when they start writing their own?